Hello. In this video, I'm going to take you through looking at a problem from a couple of different lenses. So this problem is your cousin Throckmorton pulls a 50-kilogram box at a constant acceleration across the floor. He applies a 200 Newton force at an angle of 30 degrees. There is a 25 Newton force of friction resisting the motion of the box. The box starts from rest, and Throckmorton pulls the box for 15 seconds. What is the final velocity of the box? So the first perspective I'm going to use is the unbalanced force on a particle model, or UFPM. So I know I have to use the unbalanced force model rather than the balanced one because this box has a constant acceleration. So the first thing I'm going to do is get myself a free body diagram. And I like to do my free body diagram right on the picture of the problem because it helps me keep track of information and how some of these forces should be related to each other. So I've added that tension force, and sometimes it can be useful if there's a lot of information to cross things out in the text of the problem as you add them to the diagram. So I have that 200 Newton force at an angle of 30 degrees accounted for in my diagram, so I don't really need that in the problem anymore. I'm also going to go ahead, add that 25 Newton force of friction. Now, I'm going to go ahead and add a force of gravity as well. Actually, I should put my label on the other side here. Now, I happen to know the force of gravity is m times g. And this is a formula that's on your formula sheet, so not one you need to have in your head. The mass of this box is 50 kilograms. And then g is always 10 newtons per kilogram, as long as we're near the surface of the Earth. If I do a quick look at my units, those kilograms are going to go away, and I'm left with units of newtons. And then the last force I'm going to add, the floor or whatever this box is getting pulled across is being compressed by the box. And so there should be a normal force acting on that box. Next thing I'm going to do is my vector addition diagram. So when I do my vector addition diagram, I'm rearranging these forces, but I need to keep them pointed in their original direction. I'm also making sure I add labels as I go so I can keep track of what each of these forces represent. So I'm not having just blank arrows on my diagram. Now, when I'm adding my force of friction, I went ahead and I left my shape open. The reason I did that is because that box has a constant acceleration. So that means that my vector addition diagram can't be a closed shape. I do like to add an arrow showing my net force. So I know that with the way Throckmorton is pulling, any leftover force should be pointing to the left. That's the direction that this box is going to accelerate. So I'll go ahead and add an arrow that represents the net force pointing straight to the left. Now that I have my vector addition diagram, I can use it to find how big is that net force. So if I imagine a triangle where this tension force is the hypotenuse and this dashed line is the base, my force of friction plus my net force, these arrows must be the same, these arrows combined must be the same length as this dashed line. So this is going to let me set up some math. So if I wanted to find the length of that dashed line, I would do my tension force times the cosine of 30 degrees. And then that must be equal to, I actually want to leave this as just the force of friction for now, force of friction plus the net force. Since the net force is what I want to find at the moment, I'm going to move that friction to the other side by subtracting it to get that the tension force times the cosine of 30 minus that friction force equals the net force. So then I'm going to plug in numbers, making sure to keep units attached to all of these numbers. So I've got 200 newtons times the cosine of 30 degrees minus 25 newtons. So when I do a trig function of an angle, the number I get is unitless. So I have a unitless number times newtons, which will be newtons. I have a number in newtons minus a number in newtons, which is going to give me a net force in newtons, which is exactly the unit I expect. So I've got my net force of 148.2 newtons. So now I'm going to go ahead and go to a clean page. I want to look at this problem, or now that I've got the net force, I'm going to combine what I figured out with the momentum transfer model. So I'm going to go ahead and make a note that I have found my net force is 148.2 newtons. So at this point, there are two major formulas we have for the momentum transfer model. We have that delta P, the change in momentum, is equal to force times time. We also have that P, momentum, is equal to mass times velocity. And we've figured out that we can rewrite the change in momentum as mass times change in velocity as long as we have a situation where the mass is constant. And we can say that's equal to the force times the time. So in this particular case, the force that's causing a change in the momentum, so the force that's applying some impulse, is that net force that Throckmorton is applying to the box. So I'm going to go ahead and write F net instead of just a blank force. The next thing I'm going to do, I want to try to get the change in velocity by itself, since this problem asks us to find the final velocity. So I'll divide both sides by m, and then I have delta V equals F net times T divided by m. So I'm going to jump over here. I can rewrite the change in momentum, the change in velocity as the final velocity minus the initial. So I can say the final velocity minus the initial is the net force times the time divided by mass. Now, this initial velocity, whoops, did not mean to erase that. This initial velocity is equal to 0 because we're told the box starts at rest. So this simplifies to my final velocity in this case is the net force times the time divided by the mass. So now I'm ready to plug in some numbers. My net force is 148.2 newtons. My time is 15 seconds because that's how long Throckmorton pulls that box for. And the mass of the box is 50 kilograms. So I'm going to take a little bit of a detour here to just check my units. So I have newtons times seconds divided by kilograms. So a newton is also a kilogram times a meter per second squared. So when I think through what's going to happen here, these kilograms are going to go away. And then this second is going to cancel out the squared on that other one, which leaves me with units of meters per second, which is what I expect for a velocity. So at this point, now that I know my units are good, I'm going to plug this into my calculator to get 44.5 meters per second. And that would be the final velocity of the box. Now, this is not the only way that we could take that net force and find the final velocity. So let's look at one other approach. This time, let's use the constant acceleration of a particle model. So there's a few pieces I'm going to need. Once again, I know that net force is 148.2 newtons at this point. So the first thing I'm going to use is that net force equals mass times acceleration. I'm going to go ahead, get the acceleration by itself. So I can take F net divided by the mass of the box is going to equal the acceleration of the box. So I have 148.2 newtons over 50 kilograms. If I do my quick unit check, a newton divided by a kilogram, that newton is also a kilogram times a meter per second squared. So those kilograms go away, and I'm left with just meters per second squared as my unit. That is exactly the unit that I expect for acceleration. So I plug this into my calculator to get 2.96 meters per second squared. The next thing I'll do is sketch myself a velocity versus time graph. So this box starts with a velocity of 0 and then accelerates at a constant rate. So the rise on this graph is going to be my velocity, or my change in velocity. My slope will be the acceleration, which I know is 2.96 meters per second squared. And then my run, how far across the bottom, is my time, which is 15 seconds. So now I can set up an equation based on the slope of this graph. So I know that slope is rise over run. But on this graph, the slope represents the acceleration, the rise represents the change in velocity, and the run represents the amount of time. I want to find that change in velocity if I'm going to figure out what's the final velocity. So I'll multiply both sides by time to get that time times acceleration equals change in velocity. I can also say time times acceleration equals the final velocity minus the initial. Once again, that initial velocity is 0. So I can get this to time times acceleration equals final velocity. I'll go ahead and plug in numbers. I've got 15 seconds times 2.96 meters per second squared. Here my unit check's a little simpler. I've got seconds, and that's going to cancel with the squared on that second squared. And that leaves me with units of meters per second, which is exactly what I expect. So I plug this into my calculator, and once again, I get 44.5 meters per second, which is exactly what I got using the momentum transfer model. And so it turns out that both of these models work equally well for finding the final velocity. They're just different ways of thinking about it. So there's an example of how we can use different models to look at the same problem in some different ways.